So finally, when we're looking at permutations, you can have multiple cases. And one way that we can identify that the problem is dealing with multiple case permutations, or that we have to perform multiple case permutations, is in the vocabulary. So if you see any part of the question that mentions either, / or, at least, at most conditions, then that means that we have to split into cases. We're going to solve each case or each permutation separately, and then we're going to add them together. So anytime you see any of this, you're solving permutations separately, and then you're going to add them together. If we look at the first one here, it says, how many arrangements of the letters in brick are there if B must be at one end or K must be at one end? So I can split this into two cases. One where the B must be at one of the ends, and the other case where the K must be at one end. So if I look at case 1, where your B is at one of the ends, so B at one end, so either the beginning or the end. Well, there are 5 items to arrange in the word brick, right? 5 letters. So if I kind of put B at either of the ends as one group here, or one thing, one item in its entirety, and I'll put that first, so B at one end. Then that leaves the other 4 letters to arrange. So I'm going to put it like this. Now, the B at either end, it could be at the beginning or it could be at the end. So it has 2 possibilities. Then with the rest of the 4 letters, once we use one, we cannot repeat. So it's just be 4, 3, 2, 1. And so the permutations for the B at one end would be about 48 arrangements. And that's for the first case. Now the second case, where the K is at one end, it's the same thing. The K could be at the beginning or the end. And so it's going to have 2 possibilities, and we're going to group it as one item. The fact that it could be at any side of the word is one item, which leaves us with, again, the remaining 4 letters to arrange, which would be 4 factorial. So 2, and then 4, 3, 2, 1. And then just like the previous case, that too is going to have 48 arrangements. But there's a third case that isn't obvious at first. And this would be that both B and K would be at the ends. Because there isn't a restriction listed here that they can't be together. They just gotta be at either end. So both of them at either end is also a possibility. And with that, if you're bringing them both together, you could have BK or KB. So this has 2 permutations. Now, if K and B are at either ends, then that leaves 3 letters of the 5 to be rearranged. So the remaining, I guess, arrangements would be 3 factorial. And I'll write here for remaining. And so for case 3, because it's both you're arranging the 3 remaining letters and BK or KB at the ends, your total permutation here is going to be 3 factorial times 2 factorial. And that would be case 3. So 3 factorial times 2 factorial. And this is going to give us 12 ways or arrangements. Now, there's something to say about this double count case, though. See, some arrangements satisfy both conditions at the same time, right? Where B is at one end and K is at the other. And what happens is, we already counted those arrangements twice. We counted them once in case 1 and once in case 2. And so what we're going to do is, to correct this overcounting, we're going to subtract this overlap. Okay, and this is kind of the case of the overlap. So when we find our total permutations, we're going to go the case 1 plus case 2, and then we're going to subtract the overlap. And that's because if B, K are together at one end and together at the other end, then you're counting once again the times that B is at one end and at the other end, and K is at one end and the other end. So to avoid overcounting, we're going to subtract that overlap. So in this case, then we would go 48 plus 48 and then minus 12. And so the total number of permutations here is going to be 84. If you think about it kind of like a Venn diagram, where I would have, the left circle that represents when, the permutations of when B are at the ends, and then the right circle where K is at the ends. In the middle, you would have B and K, right? For the third case here. So I'm going to write B and K. Well, the only stuff that we would actually compute would be what doesn't overlap here. If I am, let's say, calculating the area of this circle, I would subtract, right, this part here because there's overlap. So by that same token, we're going to subtract the double counting or the overlap from adding these two here. So for some key rules here when it comes to dealing with multiple cases, any ORs, you're going to add the counts of each condition, but then we're going to make sure to subtract the counts that satisfy both or all conditions. So having both B and K at either end satisfies all the conditions of the permutation that we were talking about here. So we would subtract that at the very end. But then each permutation, B is at each end, or B at each end, and then K at each end, we add those together. Those don't directly overlap. So for the second example, how many words with at most 3 letters can be formed from the letter tiles Sunday? So the most that we're looking to form or to arrange is words that are 3 letters tops. So that allows a couple of cases. Case 1, where it's 1 letter. Case 2, where it's 2 letters. And then case 3, when it's 3 letters. And then that's where it stops. So for 1 letter word, out of 6 letters, so n would be 6, we're choosing just 1. So our permutation, when we plug it in our calculator, is going to be 6p1. And that gives us 6. For the second case, out of 6 letters, we're only choosing 2, and it could be any 2. So our permutation is going to be 6 choose 2. And that gives us 30 possibilities or arrangements. And then lastly, for the third letter, out of 6 letters, we're choosing 3. So our permutation is going to be 6 choose 3, and that gives us 120. And so it's at most 3, so you could have 1 letter or 2 letters or 3. And since the word is or, we can add each of the counts separately. So the total permutation is going to be 6 plus 3 plus 120, and that gives us 156 possible arrangements here. For our third example here, how many 3-digit odd numbers greater than 600 can be formed using the digits 2, 3, 4, 5, 6, and 7 if a number contains no repeating digits? So if the number has to end up odd, and I'm going to write this down, that means that the ones of the number, at the ones column, hundreds, tens, ones, must be odd. Otherwise, it doesn't matter what the other two numbers are. If the last number or the one digit is even, then it's an even number. So it must be odd. And secondly, it has to be greater than 6. So 600, I should say. So for the hundreds, then we have a case. For case 1 is where the hundreds is 6. Because you could have 632, it can't be repeat numbers, so 635, for example, or 625. That is still bigger than 600. And then the case 2, out of this choice here, that is going to be greater than 600, is when the hundreds start with 7, making it 700s. So if we start off with case 1 where the 100 is 6, we're going to focus on the ones at first because they're the ones that help determine if the number is going to be odd. And that would then kind of narrow the choices down to either being a 3, a 5, or a 7. And so that leaves the ones with 3 choices. Now for the tens, you can't have any repeating numbers in this 3-digit number. So that means you can't have a 6 since the 100 is already a 6. And you can't have whatever one we place between the 3, 5, and the 7. So out of the 1, 2, 3, 4, 5, 6 numbers, where the first option is already taken because the hundreds begin with 6, minus the second option, based on whatever you chose for the ones, that leaves us with 6 minus 2, the difference being the number of options for the tens. And so we take the possibilities of each event, so 4 multiplied by the other one, 3, and that gives us with 12 possible arrangements. Now, if I look at the 100, where the hundreds is 7, right below it, well, your units must be odd, but it can't be 7, because otherwise, then that's a repeating digit. So then we're only left with 2 choices for the 1. And then if we look at the tens, well, out of 6 numbers, you can't choose the 7, and you can't choose the number that you chose for the ones. So that is also going to leave us with 2 less options from what we originally started with. So 6 minus 2 is going to be 4 here. And so 4 times 8, there's 2, I should say, gives us 8. And so none of these overlap. They're completely different numbers, right? They're both distinct. 6 and 7, the 100 column won't overlap at all. So we don't have to worry about subtracting any overlaps. So for the total permutations, I'm going to write for my NPR, and we'll section it off here. That is going to be equal to case 1, which had 12 possibilities, plus case 2, which had 8, giving us 20 possible numbers.